Since 1933, scientists have theorized the existence of an invisible substance which makes up the majority of the matter in the universe. This hypothetical material was coined the term dark matter and is used by cosmologists and astrophysicists to explain numerous perplexing natural phenomenon, particularly with the dynamics of galaxies, as well as other observations such as lensing effects. But why did it take all the way until 1933 for dark matter to be proposed? And in the almost 100 years since its ideological inception, why has humanity yet to experimentally record its existence? This video will attempt to answer such confounding questions and give you an overview of dark matter. Firstly, I want to discuss why we even need to include dark matter in our universal theories. It definitely wasn't just thought up out of the blue because it sounds cool and uncanny. Early estimates of the masses of galaxies in the late 1800s and early 1900s were made through measuring the luminosity and inferring the velocity distribution of stars around their galactic centres. This can be done by analysing the light from them here on Earth. For example, hydrogen has a tendency to release photons of light of 21 centimeters over time. This is a quantum effect based on how the electron is arranged in high energy states and flipping to lower, releasing light. The Doppler shift of this light from galaxies can be used to determine the rotation curve of galactic disks, which can then be used to estimate the mass. Well, it turns out that these estimates for the mass of galaxies was much higher than the observed mass from estimations from the light. One can estimate that each star is similar to the Sun, whose luminosity or light power output and mass we know. So from recording the luminosity of a galaxy, we can compare this to how many Sun-like stars that would correspond to, and thus infer an estimate for the mass. As intrinsically, mass and luminosity are related, but that's a topic for a future video. Now obviously not every star is the same as the Sun in terms of mass nor luminosity, however as an estimate it's not bad. You can use similar arguments and get other estimates for masses of galaxies, but the point remains. The estimated mass from analysis of velocity distributions is way higher than any estimate from stellar or star mass. The ultimate conclusion was that there must be some unseen matter which is contributing to the velocity distribution of stars. Since the speed at which stars orbit the galactic centre is due to gravitational forces, one can make the argument that the dark matter must act gravitationally but cannot be seen. This is a key feature of dark matter. It doesn't interact electromagnetically, only gravitationally, don't forget it. Remember that light of every frequency is merely the result of an electromagnetic interaction, and since this matter is invisible, it must not interact electromagnetically, hence use of the word dark. Anyway, this wasn't the only issue which hinted towards the existence of dark matter. In the 1960s and 70s, calculations of rotation speed of stars as a function of distance from their galactic centre were able to be completed and analysed. What was discovered was quite shocking. Also in simpler terms, this is essentially the speed at which the stars are moving as you get further away from the centre of a galaxy, which is what they're orbiting. Stars don't seem to drop off in an inverse square law with distance to the centre, which is what one would expect. This is how classical gravitation works and results in the orbital velocity squared being proportional to the inverse of distance. For context, this is known as Keplerian rotation, and is how every planet in the solar system behaves. So why is this not the case on galactic scales? You may think instead the rotation could be rigid, like the stars are connected on a solid line which turns with constant speed. This makes the stars at the furthest points move quickest as every star is rotating at the same angular velocity. This is the case with things such as prongs on bike wheels and any solid rigid disk. But alas, this was also not the case. What was found is that the velocity distribution was roughly constant for typical distances from centres. This means that the velocity of every star was the same regardless of how far it was from the galactic centre. Needless to say, this was bizarre. No model could have predicted this, at least not one without the presence of, yep, you guessed it, dark matter. Once again, the necessity of dark matter to explain the phenomenon was incited. Now our models of galaxies look something like the following. We have a central sphere of stars, called the bulge. Then stretching out we have the disk and the stellar halo. This is where almost all the stars are confined within, and where the light from galaxies is observed. And now we have the dark matter halo, which extends even further spherically away from the galaxy. This theoretical distribution of dark matter is able to fix the rotation curve conundrum. By assuming a large amount of matter in a sphere from the centre, we can predict the observed constant speed. For reference, this is known as a flat rotation curve. Flat implying no change in the orbital velocity of stars with changing distance from the centre. This is since the graph plot of such a function is flat, so feel free to look into flat rotation curves if you want a more in-depth look. Nevertheless, the evidence in favour for the existence of more matter in galaxies doesn't end there. Since at least the 1980s, we've observed gravitational lensing. This is where mass bends the fabric of the universe known as spacetime and causes light to travel in apparent curved paths to us. This phenomenon is really weird and quirky, so much so that I've already made a video on its origins and the consensus on it. Feel free to check it out after you're done with this one. Anyway, it's an effect of general relativity, and the amount of bending of light from distant light sources is proportional to the mass of the object in front of it. So when we look at light from really distant galaxies, and there are galaxies between us and the observation, gravitational lensing takes place. This can be used to infer the mass of galaxies acting as gravitational lenses, and yep, you probably guessed it, the lensing effects are typically much stronger than we'd expect, once again pointing towards the existence of invisible mass, adding to the strength of the lens. Now we have 3 separate experiments with conclusions suggesting the presence of more matter in galaxies than what we can account for from that of the stars. And no, the mass of things such as planets and other space rocks are negligible compared to that of the stars and galaxies, and so is not what's causing the huge mass discrepancies. It has to be something else which we aren't able to observe. Now that I've discussed the almost overwhelming evidence for dark matter, you're probably asking yourself what dark matter is physically. Is it a type of particle? If so, what? Or is it something else? Well, if I had an answer to that, then there'd almost certainly be a Nobel Prize in Physics with my name on it waiting for me. The best I can give you is the current scientific consensus. Most cosmologists believe dark matter to be some kind of undiscovered fundamental particle. Could it be a baryon, a meson, a lepton, a boson, some other type of particle altogether? This is where we've hit another ceiling. The search for a dark matter particle is a major effort now in particle physics. Certain research groups have even built detectors deep under the Earth, shielded by thick lead rooms to try and detect nothing but possible dark matter particles. The idea here is that if it's so prevalent in galaxies, then surely we'd be able to find some here on Earth. Yet so far, these experiments haven't yielded any results. This could be because dark matter isn't found on Earth or near planets or ordinary matter. Or more likely, our detectors are unable to actually detect the dark matter present. Like, this particle doesn't interact electromagnetically, as we already know, and an individual particle will likely have such a tiny gravitational effect that we can't pick it up when it hits the detector. So we're at a loss here. We can't possibly know what dark matter is. Or can we? There have been theories put forward that dark matter could be particles such as WIMPs or machos. Awesome names, I know. WIMP stands for weakly interacting massive particles and are hypothetical elementary particles, which may not already be on the current standard model of particle physics. WIMPs are thought to only interact via gravity and the weak nuclear force, and are also yet to be discovered, and have recently are no longer likely thought to constitute dark matter. Machos stands for massive astrophysical compact halo object, and are thought to be bodies in space which don't emit radiation, making them hard to observe directly, but have strong gravitational effects, which account for dark matter considerations. These could be things such as black holes, neutron stars, unassociated planets, and such. These are thought to be detectable when they pass in front of stars and microlens the light around themselves. However, since machos are thought to have masses similar to that of stars or planets, they aren't nearly massive enough or possibly common enough to account for the major amounts of missing mass in the dark matter problem. So machos are also not likely to fix the issue. This is why we are still yet to experimentally detect dark matter. The hunt continues to this day and is one of, if not the biggest, unsolved mystery in astrophysics and cosmology. Taking into account the discrepancies between the amount of matter we can see in the universe and how much predicted matter there is when including dark matter gives quite a surprising ratio. Dark matter seems to make up around 5 times more of the universe than ordinary matter does. But not just this. Ordinary matter is thought to only make up around 5% of the universe, with dark matter making up another 25% or thereabout. Any of you who are quite good at maths may notice that 5 and 25 don't add up to 100%, and thus are wondering what the final 70% of the observable universe is consisted of, and the answer to such question would be dark energy. Dark energy is thought to act against gravity and cause the accelerating expansion of the universe. Again, not much is known about this mysterious form of energy, hence the name dark energy. But it's nonetheless another really interesting topic which deserves its own video, so let me know if you'd be interested in a dark energy video similar to this one. We know mass and energy are equivalent through the famous equation E=mc², ignoring relativistic effects. I know, please don't slander me in the comments. So who knows what dark energy or matter could be? Perhaps someone watching will someday figure it out and become a legend in the field. Anyway, a few common misconceptions I want to quickly clear up. Dark matter and antimatter are not the same thing. It's easy to get terms mixed up and confused, especially when you're new to learning about them, but just to make it clear, dark matter is by no means antimatter. Antimatter is proven to exist and acts to annihilate regular matter and conserve energy and momentum in the universe, at least we think. Although we know much more about antimatter than dark matter, there's still lots more research needed, particularly why there seemed to be an imbalance in the production of regular and antimatter at the Big Bang, which is ultimately how we exist at all. Again, needs its own video. Another thing to clear up is that dark matter is merely a theory. Rigorous scientific technique requires theories to be changed, peer-reviewed, tested, scrapped, etc. all the time. So just because this is what most physicists believe about the universe, it doesn't mean it's ultimately true. Someone could come along one day with a brand new theory to explain all these discrepancies, like how Einstein did with gravity. A new theory not involving dark matter would be extremely unlikely, but perhaps necessary since after all we are yet to detect any. Another interesting thing I want to add. Some of you may know that I'm a physics student about to go into my third year at university, and this year I'm going to be studying Type 1a supernovae and creating computer programs to relate their brightness to the expansion rate of the universe and analyse different models for our universe. This will involve lots of dark matter and dark energy considerations in the models I'll be using. I'm really looking forward to this project, and so I'll definitely be creating more videos on dark matter and cosmology in the future, so stay tuned for that. One final thing, if you made it this far and enjoyed the video, please consider subscribing. Only a small amount of people who actually watch my content are subscribed. It's free to do so, helps out my channel a lot, and you can always unsubscribe. But as always, thank you for watching this short astrophysics video.